Hello, George Notchik. This is part 2 of our discussion on fractional, differential, and integral calculus. This second part is now going to talk about fractional integration. Then we're going to combine fractional integration with fractional differentiation. Then I'll talk about the general fractional derivative of an exponential, of a sinusoid, and then we'll finish up by solving a fractional differential equation. Here are some of specific values of the gamma function and properties of the Laplace transform. These are Laplace transform pairs. This is the function in the x domain, like x raised to the power v, where v is a real number greater than -1. And in the transform space, the Laplace transform of x to the v is just gamma v plus 1 over the Laplace variable raised to the v plus 1, and so on. With these other transform pairs, we'll be using these, we'll be referring to these transform pairs as we proceed. Let's look at the 1/2 integral of x with respect to x. Now, as we did when we took a fractional derivative, we take our function in the x domain. In this case, we look at the integrand and we transform it into the Laplace space. You remember that x transforms in the Laplace space as 1 over s squared. Then we perform our operation of integration in the Laplace space, and then we take the result and transform back to the x space. Well, like we had with taking a derivative, when we take a derivative, we multiply by s to a power, where the power is the order of the derivative. And in a similar manner, integration goes into division in the s space. So if we're taking the 1/2 integral, we divide by 1 over s to the 1/2, where the power on s is the order of the integration. So combining the exponents, we have 1 over s to the 5/2. Now we're going to transform back to the x space. Well, what does s to the 5/2 transform to? Well, we look at this particular transform pair. We have s, 1 over s to the 5/2 times a constant, which transforms to x to the 3/2. Well, we just have 1 over x to the 5/2 alone, so we multiply both sides here by the inverse of this constant to get 1 over s to the 5/2 alone in the transform space. So then, this is going to transform to 4 over 3 square root of pi times x to the 3/2. So this now becomes, in the x space, 4x to the 3/2 divided by 3 square root of pi. So that's the 1/2 integral of x with respect to x. We start in the x space, we transform, perform our integration, our operation, then transform back to the x space. That's the procedure that we use. Now let's go one step further and look at what the 1/2 integral of x raised to the power p looks like. Well, as before, what we do is we find the Laplace transform of the integrand, x to the p. Well, we use this form here, and we have to put in for v, p. So when we put that in, we go into the transform space, And so the transform of x to the p is gamma p plus 1 over s to the p plus 1 in the transform space. That's the Laplace transform of the integrand. Now we perform the operation of taking 1/2 of an integral, or 1/2 integral of the integrand. Well, like before, is we divide through by s raised to the order of the integral. And in this case, we're dividing by s to the 1/2. And combining powers, this becomes gamma p plus 1 over s to the p plus 3/2. So that's our integrated function, the 1/2 integral of x to the p in the s domain. Now we need to go back into the x domain. So we take our transform pair and go back. Well, we can use this transform pair again because we have x to the p plus 3/2. So we need to find the v. So we just equate the exponents. We need to find v in terms of p. So we have v plus 1 needs to be equal to p plus 3/2, or v equals p plus 1/2 when we use this transform pair. So now, to find the function of x that corresponds to this Laplace transform, we have, first we take the constant, we have gamma p plus 1, and then that's times 1 over p plus 3/2, s to the p plus 3/2. Well, s to the p plus 3/2 will give us x to the v. Well, v is p plus 1/2. And we have to divide by gamma v plus 1. Well, v plus 1 is p plus 3/2. So this is our function in the x domain. Gamma p plus 1 over gamma p plus 3/2 times x to the p plus 1/2. So that's the 1/2 integral of x raised to the p power. Now we could, we also have a restriction here. We know we need to adhere to the fact that this transform pair is valid for v greater than -1. So v has to be greater than -1, or in this case, p has to be greater than -1/2 to use this. And we can see that that's going to be true, because if p is -1/2, this becomes, let's see, yeah, greater than -1/2 is because in our transform, when we went from here to here, p had to be greater than -1, because if p was a -1, we'd have gamma 0, which blows up. And so this transform pair becomes invalid when p is -1 in this case, but then we apply it a second time and we see we have a further restriction that p has to be greater than -1/2. Now, suppose p is a member of, or is an integer, n. Let's just say p is equal to n, which is an element of the positive integers. Let's see if we can, well, this becomes, we can further reduce this in the case that n is equal to an integer, because the gamma function takes on specific values when p is an integer. We'll see that here. So our two gamma functions here. Let's look at gamma. P plus 1 becomes n plus 1. And remember, gamma n plus 1 is just n factorial when n is an integer. And what about gamma of n plus 3 halves? Well, we can use properties of the gamma function. We could write this as gamma of 1 plus n plus a half. Well, gamma of 1 plus z is z times gamma z. So this becomes n plus a half times gamma of n plus a half. You could write it that way. Now, gamma of n plus a half has further reduction, and this becomes equal. You can manipulate the properties of the gamma function. We have this constant here, and gamma of n plus 1 half, if you remember, is 2n factorial times the square root of pi over 4 to the n times n factorial. So now, if we ratio these two gamma functions, p gamma n plus 1 over gamma n plus 3 halves. Remember, p is equal to n. So we're ratioing these two. So we'll have n factorial over n plus 1 half times 2n factorial square root of pi, and then we have a 4n and an n factorial on top. We have two n factorials in a product, so this just becomes n factorial squared, and then we have x to the n plus 1 half. So that is the 1/2 integral of 1/2 integral of x to the p with respect to x. So that's what we get. Or, I'm sorry, when x is n is an integer. N is an element of the positive integers. So, for example, if x is 5, we have x 1/2 integral of x to the 5th power. We put in n equals 5 here and reduce it down, and we'll have it'll be x to the 5 1/2 power times a constant for the 1/2 derivative on x to the n. For example, let's let n equals 3. So we'll have on top 3 factorial, 4 to the 3 over 3 plus a half, that is 7 halves, times 2 times n, or 6 factorial, square root of pi, and then x to the 7 halves. 3 plus a half is 7 halves. Well, we can reduce this down further. 3 factorial is 3 times 2 times 1. Then we have 4 to the 3rd, or let's write that as 4 times 16. And then we have 7 halves, and then 6 factorial. Oh, I'm sorry, this is 3 factorial squared. So I have 3 times 2 twice, so I'll put 3 times 2 there for 3 factorial squared, 4 to the 3rd power, 7 halves. 6 factorial is 6 times 5 times 4 times 3 times 2, and then square root of pi. Well, we have a lot of cancellation we can do. We have a 3 times 2, which cancels a 6, We have 3 times 2 here. The 4's cancel. The 2 comes up on top. So we have 16 times 2, or 32. And then 7 times 5, or 35, square root of pi. So for the 1/2 integral of x to the 3rd power with respect to x then becomes 32 over 35 square root of pi x to the 7/2. Now, let's take the 1/2 derivative of this. If we take the 1/2 derivative of this, then we should end up back to where we started, right? The 1/2 derivative of the 1/2 integral should give us just x to the 3rd back. Just like when we have full derivatives and full integrals. If the mathematics is consistent, we should end up with x cubed. All right, so let's take the 1/2 derivative of 32 over 35 square root of pi x to the 7/2 with respect to x. Let's find out what that is. We can pull the constants out. So we have 32 over 35 square root of pi, and we're taking the 1/2 derivative of x to the 7/2 with respect to x. Well, let's work on this. We first transform x into the s domain, the function that we're operating on. So x to the 7/2 in the s domain, well, if we look at this, x to the 7/2, here we have x to the 5/2. If you work it out, x to the 7/2, let's see, if we have 7/2, we can use this. So v is 7/2. So this becomes gamma 7/2 plus 1 over s to the 7/2 plus 1 becomes 9/2. 7/2 plus 1 is 9/2, so we'll have gamma of 9/2 over s to the 9/2. Well, what's gamma of 9/2? Well, gamma of 9/2 can be written as the gamma of 1 plus 7/2, which is 7/2 times the gamma of 7/2. Well, we have gamma of 7/2 up here, which is 15 over 8 times the square root of pi. So this becomes 7/2 times 15 over 8 times the square root of pi. And this is over s to the 9/2. So this is 105 over 16 square root of pi over s to the 9/2. That's in the transform space. That is our x. Now we take a derivative, the 1/2 derivative, so we need to multiply by s to the 1/2. So if we multiply by s to the 1/2, we subtract exponents. So we have 105 over 116, or over 105 over 16 times the square root of pi over s. 9/2 minus 1/2 is 8/2, or 4. Now, what does this transform to in the x space? This is the integral, or this is the 1/2 derivative of the function 32 over 35 x to the 7/2 square root of pi. This is the 1/2 derivative of it in the s space. Now we go back and we look at this, In this case, s is raised to the power 4, so v is 3 in using this transform pair. So when v is equal to 3, we can write this. I'll just do another step here. So x to the third becomes gamma 4 over s to the 4. That's the transform pair. X to the third becomes this. So we can write 1 over s to the fourth transforms then to x to the third divided by gamma to the gamma of 4. But remember, of an integer, gamma of 4 is 3 factorial. So this becomes x to the 3 over 3 factorial. That's the transform of 1 over s to the 4. Well, this gamma of 4, again, is 3 factorial over s to the 4. And then s to the 4, we multiply by 3 factorial. And our 3 factorials cancel, and we end up with x to the third. Just what we started with. The 1/2 integral of x to the third was this. And then we take the derivative of this, 32 over 35 divided by square root of pi x to the 7/2. 1/2 derivative of that ends up being x to the third. So we're back to where we started. So it is consistent. If we take the 1/2 derivative of the integral, 1/2 derivative of the 1/2 integral, we just have the same function back. It's just like taking the derivative of the integral of f of x, and that's f of x. And that's the same thing. The 1/2 derivative of the 1/2 integral of f of x with respect to x is f of x. It's consistent. So we get our integrand back. If we take the rth derivative of the rth integral, we just end up with the function back, just like with normal calculus. Now, when we indefinitely integrate a function with respect to x, we get an antiderivative plus a constant when we're dealing with whole integrals. Now, let's investigate to see if that's true with fractional calculus. Now remember, in standard calculus, if we take the indefinite integral of, say, some function of x with respect to x, we get the antiderivative of f plus an arbitrary constant. The constant is added because we get the same original function back, f of x, that we start with when we differentiate the antiderivative. If we differentiate this, the fundamental theorem of calculus tells us that the derivative of f of x with respect to x is the integrand f of x, and we know that the derivative of a constant with respect to x is 0. So by adding an arbitrary constant, we know that in indefinite integration, the antiderivative is always found within a constant of the actual function. And to find what the value of the constant is, we'd have to have specific limits on the integral in order to evaluate the constant. Now, the question that we need to pose is, can we add a constant to the indefinite fractional integral? And that depends upon what the fractional derivative of a constant is. If the 1/2 derivative of a constant is 0, then when we're taking the 1/2 indefinite integral, we could add the constant if the 1/2 derivative is 0. But we found that the 1/2 derivative of a constant is not 0. that the 1/2 derivative of a constant a, say with respect to x, comes out to a over the square root of pi x, not 0. So we cannot add a constant to the indefinite fractional integral. In general, we can't do that. So now we have to ask ourselves, is there a function whose 1/2 derivative is 0, or actually an impulse function that is 0 everywhere except at x equals 0, that can be added to the 1/2 integral so that it will not affect the result when the 1/2 derivative of the antiderivative is taken? What I'm saying here is, remember, when we take an indefinite integral, a full integral on a function, we add an arbitrary constant. And we found that we cannot do that, say, with the 1/2 integral. The 1/2 integral on f of x with respect to x is some new function, let's call it h of x, plus, say, if we add a constant and we now take the 1/2 derivative of this, we have a problem. If we take the derivative of the 1/2 integral of f of x, we're taking the 1/2 derivative of h of x plus the 1/2 derivative of a constant. Well, we found that the 1/2 derivative of a constant is not 0. That the 1/2 derivative of a constant, let's just call it a to differentiate it, a little different from the arbitrary constant we had with the full integral. We'll call this, we're adding an arbitrary constant a, but we know that the half derivative of an arbitrary constant is not 0. It goes to a over the square root of pi x. That is the 1/2 derivative of a constant. So we cannot add a constant to the 1/2 integral, because when we differentiate the antiderivative, the half derivative of the constant does not vanish. It is actually a function, a over the square root of pi x. So the question that is we need to ask, is there a function that we can add to the antiderivative such that when we take the 1/2 derivative, it vanishes? So what we're asking here is there something we can add, let's call it g of x, is there a g of x that we can add such that when we take the 1/2 derivative of g of x, this goes to 0, and we end up with our integrand back, our f of x. That is, we're taking the 1/2 derivative of f of x, we get some function h of x, and we're going to add an arbitrary function to it. And then when we take the 1/2 derivative of this, we're taking the 1/2 derivative of our antiderivative plus the 1/2 derivative of this arbitrary function we're adding, and this is going to vanish, and the 1/2 derivative of h of x is just the 1/2 derivative of the antiderivative, which is the integrand back. So we need to determine what is that arbitrary function we can add to an arbitrary 1/2 integral such that when we take the 1/2 derivative, it vanishes. Well, the answer is g of x is just going to be 1 over the square root of x. Now, we can see that 1 over the square root of x is x to the 1/2. Well, what's the 1/2 derivative of x to the 1/2? Well, here's the transform pair. So, we transform x to the minus 1/2 into the transform space, into the s space, and that becomes the square root of pi over s to the 1/2. Now, when we differentiate it 1/2 times, we take 1/2 derivative of g of x, and in the transform space, we're multiplying by s to the 1/2. So we have square root of pi times over s to the 1/2, and then to perform this differentiation, we multiply by s to the 1/2. Those go out, and we have the square root of pi in the s domain, and that transforms into the x domain as the square root of pi times the delta x, but the impulse function is 0 everywhere, except right at x equals 0. So this is equivalent to saying that the derivative on g of x, the 1/2 derivative of g of x, is 0. So what we add then to the 1/2 integral, if we perform a 1/2 integration on some function of f of x, we get the 1/2 antiderivative plus we add square root of pi over the square root of x. That's like adding the arbitrary constant in with the full derivatives. So when we take the 1/2 derivative of this, we just end up with f of x, because the 1/2 derivative of this vanishes to 0, and the 1/2 derivative of the 1/2 antiderivative just gives us the function back, the integrand back. Now, how about if we figured out what the 1/2 integral of x to the p was? This is our h of x, which was the 1/2 integral of x to the p. Now let's take the 1/2 derivative of this and see if we end up back to x to the p. So we're going to take the 1/2 derivative on h of x with respect to x. Well, again, we have to transform into the s space. So we're going to take this function here. This is our h of x, and we're going to differentiate it 1/2 time with respect to x. So this then goes into the transform space. The constant transforms over, and then we're find the Laplace transform of x to the p plus 1/2. Well, we use this right here. In this case, x to the v is p plus 1/2. So our v equals p plus 1/2. So the x transforms to v, or gamma of v plus 1. Well, v plus 1 is p plus 3/2. So wherever we have v, we put in p plus 1/2. Where we see v plus 1, we put in p plus 3/2. So this becomes gamma p plus 3/2 over s to the p plus 3/2. So now we're in the transform space. This is our h of x. Now we're taking the 1/2 derivative of h of x, so we multiply by s to the 1/2 to take the 1/2 derivative to perform that operation in the s space. So this now becomes, we can subtract the power 1/2 from this, so p plus 3/2 becomes p plus 1. 3/2 minus 1/2 is p plus 1. So that's our 1/2 derivative. Now we transform back to the time domain, or to the x space, to see what function of x this represents. Well, we can use this. We have 1 over s to the p plus 1. And in this case, we make our v equal to p. So then this becomes, if we look at, first we can see a reduction here. We have p plus 3/2. Those go out in the numerator and denominator. Then we have x to the p becomes gamma p plus 1 over s to the p plus 1 using this transform pair. Well, we need to move our gamma p plus 1 over to this side. So 1 over s to the p plus 1 transforms to this. So we take our derivative in the s space. The derivative in the s space is gamma p plus 1 over s to the p plus 1. And this is now going to transform into the x domain. We're multiplying 1 over s to the p plus 1 by gamma p plus 1. So we have gamma p plus 1 times the transform of 1 over s to the p plus 1, which is x to the p, divided by gamma p plus 1. The gamma p plus 1's cancel, and we end up with x to the p. So we're back to where we started. We took the 1/2 integral of x to the p. We got this function. Then we differentiated it 1/2 times, and we ended up back with x to the p. So it is consistent. If we take the 1/2 derivative of the 1/2 integral, we end up back where we started. Now let's see what happens when we take the 1/2 integral of the 1/2 integral of p to the x. So what we're going to do here is we're going to take the 1/2 integral again on the 1/2 integral of p to the x with respect to x. Now, if the mathematics is consistent, the 1/2 integral of the 1/2 integral ought to be the full integral on x to the p with respect to x. And we know what this is. We just raise x to the power 1. We raise the power by 1 on x and divide by that power. So that's the full integral on x to the p. Now, if we integrate this 1/2 times, we should get this if the mathematics is consistent. So what we're going to do now is we're going to take the 1/2 integral on this. So I can pull the constants out in front. So I have gamma p plus 1 over gamma p plus 3/2. And we're going to take the 1/2 integral of x to the p plus 1/2 with respect to x. So let's work on this and see what we end up with. Well, first thing we need to do is we have to first transform the integrand into the Laplace space, then perform the 1/2 integration and transform back. Well, what is the transform of x to the p plus 1/2? Well, we use this right here. So we know that x to the v transforms to gamma v plus 1 over s to the v plus 1. Well, in this case, v is p plus 1/2. So wherever we have v, we're going to substitute in p plus 1/2. So we'll put p plus 1/2 here. P plus 1/2 plus 1 is just p plus 3/2. So we have p plus 3/2. And v plus 1, remember our v is p plus a half, so this is also p plus 3/2. So that is x to the p plus 1/2 in the s space. Now we integrate. To integrate 1/2 times, we divide by 1 over s to the 1/2. That's the 1/2 integral in the Laplace space. Well, we can combine the exponents on s, and this becomes p, or gamma p plus 3/2 over s to the p plus 3/2 plus 1/2, which is 4/2, or just p plus 2. So now we have performed the integration. Now remember, we're just operating on this portion here. We're taking the 1/2 integral of p plus 1/2, and that's the integral here. We've multiplied by 1 over s to the 1/2, and this is our result. So now we go back to the x space. Well, to get back into the x space, to find what this 1/2 integral represents, this becomes gamma p plus 3/2, and now this is times 1 over s to the p plus 2. So now we need to look at what that is in the x domain. Well, in this case, we have, if we look at this, p, or v would be p plus 1 to give us p plus 2 here. So I can look at this transform pair again, and what I'll do is this. I'll look at 1 over s to the v plus 1, and this transforms to x to the v over gamma v plus 1 using this transform pair. I just brought the gamma v plus 1 down. Now we have a s to the p plus 2, so then this, our v, needs to be a p plus 1 to give us p plus 2. So this becomes p plus 2, p plus 1, gamma p plus 2. Okay, again, looking here, v is just p plus 1, so wherever we have v plus 1, we have p plus 2. And wherever we have v, we have v plus 1, or p plus 1. So this is this portion transformed back into the x space, but we need to multiply by this constant. We actually have here gamma p plus 3/2, so we multiply each side by p plus gamma p plus 3/2. Now we put it in. We can see now what we have. This is the integral. That is this integral. The integral of p, the 1/2 integral of p x to the p plus 1/2 is this. So let's put it all together. So then this becomes gamma p plus 1 over gamma p plus 3/2. That's this portion here. And then the integral of x to the p plus 1/2 is this, which is x to the p plus 1 gamma p plus 3/2 over gamma p plus 2. Well, our gamma p plus 3/2 go out, and remember that, let's see, we've got gamma p plus 1 times x to the p plus 1. Remember, gamma p plus 2 can be written as is gamma 1 plus p plus 1, which is p plus 1 times gamma p plus 1. So this gamma p plus 2 is p plus 1 times gamma p plus 1. And look what happens. The gammas drop out, and we have x to the p plus 1 over p plus 1, which is the full integral on x to the p. So it is consistent. So the 1/2 integral of the 1/2 integral is just the full integral, as we would hope it would be. Now, I'm going to look at the general exponential function. And in order to do that, to find the 1/2 integral on an exponential, we need to look at what's called the incomplete gamma function. So the incomplete gamma function is defined this way. Gamma of z x, or let's zx is equal to the definite or improper integral on x to infinity of t to the z minus 1 e to the minus t dt. And like the gamma function, there's only very specific values of z and x in which you can evaluate that. Now, there's also another incomplete gamma function, complementary, called small gamma of z x, which is 0 to x of t to the z minus 1 e to the minus t dt. So we can see that gamma, cap gamma on zx plus gamma, small gamma on zx, is just the integral from 0 to infinity of t z minus 1 e to the minus t dt, which is gamma z. So that's the relationship. The gamma function complementary or incomplete gamma function and its complement, the sum gives you the ordinary gamma function. Now there's some relationships involving the incomplete gamma function. There's gamma of z plus 1 x, and there's a reduction formula like for the regular gamma function. That is, gamma of z plus 1 on x is just z gamma zx, and then we have this added term here. And a useful relationship is that the incomplete gamma function of 1/2 on with x is the square root of pi times the complementary error function of square root of x. And the incomplete gamma function on 1x is e to the minus x. So those are useful relationships there that we can use. Now let's find the 1/2 derivative of an exponential, e to the kx. So we're going to take the 1/2 derivative of e to the kx. Well, as before, the first thing we do is we transform the function we're taking the derivative of into the Laplace space. Well, e to the kx transforms to 1 over s minus k. you can use this form here to see is if v is equal to 1, we have x to the 0, and gamma of v equal to 1 is 1. And if we make a equal to minus k, we have e to the kx, and v is equal to 1, so we have s plus a, but a is minus k, so it's 1 over s minus k. That's the transform for e to the kx in the Laplace space. Now, when we take the 1/2 derivative, we perform the operation in the s space by multiplying by s to the 1/2. So, the integrated function, the integral, the 1/2, or not the integrated, but the differentiated function on e to the kx in the Laplace space is s to the 1/2 over s minus k. And if you look up the transform pairs, this function in the s space becomes e to the kx, k to the 1/2 times 1 minus the complementary gamma function of minus 1/2 kx over gamma minus 1/2. So that is the 1/2 derivative of e to the kx in the x space. And I'll show you later at the end of the video what this reduces down to. It comes down to a very nice form. Now, what about a trig function? What about the, say, 1/2 integral of sine x? What's that? Now, I need to remind you that in order to use fractional calculus and perform it effectively, you really need to have a book on transform pairs, because you don't want to be performing all these integrals, these complicated integrals, to get the function in s in the Laplace space and then transform back using the inverse transform. That's really nasty stuff, and you want to make work easy for yourself, so it's always handy to you want to have a book of transform pairs so that you can easily go from the x domain to the s domain and then back by just looking up what the pairs are, the transform pairs are in the tables. So let's take the 1/2 integral of sine x with respect to x. Now remember, I talked about at the beginning of part 1 where the exponential form of defining fractional derivatives and integrals isn't very satisfying. In fact, it's very simple. It's a simple-minded way of doing things, which ends up giving you a sine or a cosine function that just phase shifts to the right or to the left. But it has very limited use. You can't solve fractional differential equations with these sorts of exponential definitions for fractional calculus. Now, what we're going to do is we first, remember, we transform our function into the s space. So sine x transforms into the s space as 1 over s squared plus 1. Then we're going to take the 1/2 integral. So taking the 1/2 integral on this, we multiply by 1 over s to the 1/2. So the transformed function of the integral is s squared plus 1, 1 over s to the 1/2 times s squared plus 1. Well, the inverse transform of this, to get the function of x that represents, you need to look it up in the table of transforms, and I'll give you what it is. The 1/2 integral of sine x with respect to x is the square root of 2 times the Fractional c integral on 2x over square root of 2x pi times the sine of x minus the Fractional sine integral of the square root of 2x over pi times the cosine of x. And the Fractional c integral on u is defined as 1 over the square root of 2 pi, the integral 0 to x on the cosine of u over the square root of u with respect to u, and the Fractional sine or s integral is 1 over the square root of 2 pi, integral 0 to x of the sine u over square root of u du. So that is the 1/2 integral of sine x, is this complicated form. Sometimes these fractional derivatives and integrals do not work out to very nice forms, or they're not intuitive anyway. You really have to work at it to get them. Now, let's solve a 1/2 order differential equation. First, let's look at a first order differential equation. First order. If we have dy dx plus ay is equal to a constant k, the solution is y of x equals e to the minus ax plus k over a. And we can see that if we take the first derivative, y primed, this becomes minus a e to the minus ax, and this is a constant, so that goes out. So if we multiply this by a and add it, the a's go out, and we add these two, y prime plus ay, those go out, and we're left with k. So indeed, that is the solution. Now, let's look at a 1/2 order differential equation. We have the 1/2 derivative on y with respect to x plus ay equal to k. What y satisfies that equation? Well, we first Laplace transform this. So the Laplace transform of the 1/2 derivative is s to the 1/2 cap y of s. We take the transform of y of x, and it becomes cap y of s, and we multiply by s to the 1/2 to get the 1/2 derivative. The Laplace transform of a y of x becomes a cap y of s, and the Laplace transform of a constant is just the constant divided by s. We factor out the y of s, so we have s to the 1/2 plus a equals k over s. Or, in the Laplace space, the solution to the differential equation cap y of s is k over s times s to the 1/2 plus a. Now, this is the solution in the Laplace space. So now we transform into the x space, and to get this, if you have a copy of Roberts and Kaufman table of Laplace transforms that I showed you in the first video, this is from the 1966 edition, the first edition, on page 212, form 52. tells us that, we'll write it up here, tells us that the transform s times s to the 1/2 plus a goes to 1 over a 1 minus e to the a, the complementary error function of a x to the 1/2. So that is the solution, but in to this differential 1/2 order differential equation. Y of s is k, or we have to multiply through by k here to get it to look like this. So the solution to this 1/2 order differential equation is this function, k over a times the quantity 1 minus e to the a, e to the a squared times the complementary error function of a x to the 1/2. Here is, I told you I would show you how to reduce down the 1/2 derivative of e to the kx with respect to x. If you remember, this became e to the kx, k to the 1/2 times 1 minus the incomplete gamma function on minus 1/2 kx over the gamma of minus 1/2. Now, this reduces down into a simpler form. Now, keep in mind, one of the properties on the gamma function was that gamma z plus 1 is z times the gamma of z. So if we make z equal minus 1/2, then this becomes gamma 1/2 equals minus 1/2 gamma minus 1/2. Well, the gamma of 1/2 is a square root of pi. So then, gamma of minus 1/2, solving, multiplying through by a minus 2, this gives us minus 2 square root of pi. So the gamma minus 1/2 is minus the square root of pi. Similarly, on the incomplete gamma function, we have a reduction relationship there, that the gamma of z plus, or incomplete gamma function on z plus 1u is z times the incomplete gamma function of z u plus u to the z e to the minus u. Now, on this, we'll let z equal minus 1/2 and u equal kx. If we do that, you'll see that this part becomes the numerator. So putting in z equal to minus 1/2, minus 1/2 plus 1 is a positive 1/2, and u becomes kx, equals minus 1/2 gamma minus 1/2 kx plus kx raised to the minus 1/2 power e to the minus kx. Now, let's multiply through by a minus 2. If we multiply through by minus 2, we get rid of that there, and then we have a minus 2 there. And let's solve for that particular form, which is the numerator here. So incomplete gamma function of minus 1/2 kx then becomes, we'll move this to the left side, so this becomes a positive. So that's 2 kx to the minus 1/2 e to the minus kx minus 2 gamma 1/2 kx. Now, this incomplete gamma function has a nice form. I gave that to you earlier, that this gamma 1/2 kx is the square root of pi times the complementary error function on the square root of kx. That's what that part is equal to, right there. So we can put that in. So we have that the gamma, or incomplete gamma function on minus 1/2 kx is equal to, I'm going to put this in the denominator, so we have 2e to the minus kx, x to the, or kx to the minus 1/2 is just the square root, 1 over the square root of kx, and then we have minus 2 times the square root of pi times the complementary error function on the square root of kx. So that's this form here. Now, let's put it all together. We see we have the denominator, gamma of minus 1/2 is minus 2 square root of pi, and then we have this form here. So let's divide this through by gamma minus 1/2, which is minus 2 times the square root of pi. So we have minus 2 square root of pi there, minus 2 square root of pi there. Now we see our minus 2 square root of pi's cancel. This becomes a plus, and our 2's cancel here. So this becomes then the complementary error function on square root of kx. This is a positive term now, minus, we have this minus in the denominator, so this is minus e to the minus kx over the square root. I'm going to write this as pi x times the square root of k. We have the square root of kx pi, and I'm just going to split it up in that fashion. So now we're almost there. Get rid of this portion. So we now can write, we have e to the kx, this is square root of k, times 1 minus this portion. And that is this. This here is this. So it's 1 minus the complementary error function on square root of kx plus, we've got a minus minus, e to the minus kx over square root of pi x times the square root of k. Now multiplying through, we have e kx square root of k minus e or let's leave that a moment. Let's do this first. 1 minus a complementary error function is the error function. Remember, complementary error function plus the error function is equal to 1. So we can take this portion here and write it as the error function of square root of kx plus e to the minus kx over square root of pi x times the square root of k. Now, let's go one step here. I can get rid of this. And we can write that multiplying through, this is equal to e to the k x square root of k error function on the square root of kx plus, we have e to the kx, e to the minus kx. So adding exponents, we have e to the 0, which is 1, and we have a square root of k and a square root of k in the denominator. So this just becomes 1 over the square root of pi x. So that's the result. There is the 1/2 derivative of e to the kx with respect to x is equal to that. E to the kx times the square root of k times the error function on the square root of kx plus 1 over pi x, the square root of pi x. So that's it. So that's as far as I'm going to take the fractional calculus for now. Hope you've learned something. The best way to treat fractional derivatives and fractional integrals is to transform everything into the Laplace space, perform your operations of integration, differentiation in the Laplace space, and then transform back. It's very, very easy, very slick.